All right, awesome. So it is my great pleasure to introduce Blockdev who is working at the privacy and scaling explorations team with the Ethereum Foundation. We have collaborated several times in the past, and we are really excited to have Blockdev today, giving us some tips for safe Circom circuits, which I hope you guys find useful, and it will be like a great complement to what we have already been discussing the whole week. So, without any further ado, please, Blockdev, take it away.
Yeah, thanks, Kostas. So yeah, hi everyone. Again, as the slide says, I'm going to present some tips for writing safe Circom circuits. This is probably going to be the most basic of the presentations we've seen so far, but yeah. So let's start. Yeah, before going in directly into the tips, I just want to emphasize, the importance of writing docs here. So this is, applicable everywhere and will be useful for anything you code. But I'd say it's slightly more important here as, Circom or any ZK language is not a general purpose language. So you may not be able to figure out what's happening without any docs. And then it's always a good exercise to have as many eyes as possible on your design doc, basically because many design flaws can be eliminated at this stage itself. And the later you delay this process, the harder it is to go back and fix them. So as an example, you may find out that something is leaking privacy, which is not the intention. So, it's always better to fix that at this stage. You might have heard of this approach as a shift left approach in security, where you try to begin your security process as early as possible. And peer review is one of those ways. You'll also find it helpful when you're actually writing the code or reviewing the circuits to go back to something as a reference. It always helps. And then the same thing is for comments. I know it's a basic advice, but heavily comment your circuits, because the same thing, it may not be obvious when you're just doing multiplication and addition of your signals. So you may not be able to find out what the developer actually meant. So just comment as much as possible. Now, with that out of the way, I'll just briefly go over this ZK stack. So bugs in ZK can be across different layers in the stack. It's the same thing as any coding stack that you have. Like in general, you have OS, then you have a compiler, then you have a code in high-level languages like Rust or Java, and then you can have bugs in any layer of the stack. It's the same thing here. You have the underlying ZK theory like Groth16, Plonk, or Stark, which forms the basis of all things that you're building on. And then you have Circom or Rust framework for Halo 2 or Winterfell, which actually implements that theory and allows developers to write circuits at a very high level and abstract it away from all the basic math. So for example, if you're writing in circuits, then you are the third bullet point here, where you're writing the application. And this is the layer which is easiest to start with for anyone if you don't have a cryptography background. And then slowly, if you're interested, you can work your way across the different parts of the stack. But application level is the easiest without any, especially if you're a developer. And this presentation is focused only on the application layer right now, just because we are focusing on Circom. So, basically, what is ZK? ZK is proving some computation to a verifier without the verifier running the computation itself, right? And with this, you have a different category of bugs. So one bug is that there's some kind of privacy bug where a property is expected to be private, but your application is leaking privacy in some form. Like you may be under constraining a signal. You may have made a private input supposed to be, which is like an input which is supposed to be private, a public input, or it may be due to your design choices that something is leaking privacy, but it should not. And the other class of popular bugs is that you are letting your verifier verify some incorrect computation, or you're rejecting some correct computation. You may have heard of this as being called soundness and completeness. So I just, again, to reiterate, yeah, these are the three classes of bugs. You can have many other bugs, but this is the common class of bugs we have. Then you have different type of circuits, and each type of circuit may require different level of expertise to find bugs. So for example, like you may be writing some cryptography primitives like ECDSA or some hashes. Here, along with verifying that your implementation is correct, you may also want to first review the design or know what are some foot guns in ECDSA, for example. Like, is it possible to generate multiple signatures for the same data and for the same signer? Is it possible that your hash that you're implementing is not does not provide strong uniqueness guarantees, and so on? So this comes with like reading lots of stuff on those algorithms or something, and it comes with experience as well. The second class of circuits you might be writing is libraries. So libraries can be called in ways that the devs might not have imagined you to. Like, for example, does the library developer place any assumption on the kind of input signals it may be receiving? Is there any preconditions for the libraries that they have not explicitly constrained for, but they expect the developer developing on top of it to take care of? So all of these things you need to be aware of as well. And then finally, you have user applications like Tornado Cache, like shielded pools, or even, I mean, ZK rollups. Yeah, it might be called as infra, but for the purpose of this presentation, let's call it an application. So all of these have bugs in their designs as well. So yeah, and again, sometimes it might not be a clear demarcation. You might be writing libraries and applications at the same time as well. But these are the kind of circuits. And moving on. So yeah, this slide is a bit of a deviation, but before moving on in your ZK journey, I'll just encourage all of you to get some understanding of elliptic curves. Just because they are so basic and they come up again and again in at least in the ZK Snark world. So for example, ECDSA signatures, Ethereum keys, hashes, many of them are based on elliptic curves. And if you become a full-time security reviewer, for example, you may have to review elliptic curve based implementation at some point. So yeah, better just get that out of the way sooner. Yeah, and now I just now the rest of the slides are practical advices on how to either catch bugs or write safe Circom circuits. So yeah, first, so while reviewing any complex circuit, I'll advise you to mentally segregate the proving and verification side. Because usually the application developer only controls the verifier, and anyone can compute and generate a proof. So that this is a very adversarial setting where you are a verifier and anyone can submit any data to you for verification. So as a reviewer, if you focus on both at the same time, you may start making incorrect assumptions about signals. I mean, this is just like a very simple example I've placed here. So like two signals are multiplied into C. So again, this is both computing and constraining at the same time, but you may want to split it out just to see what's actually happening. And to have a more complex example here, so these are just two input signals, A and B, and you want to compute and verify that you are calculating the quotient and remainder for A divided by B correctly. So what it first does is it calls a function, quotient and remainder, passes in A and B, and then calculates the quotient by A/B and remainder by A modulo B, and stores it in QR, which is an array of true size. And then it applies a division math formula by saying A is constrained to be QR0 into B, which is quotient into B plus remainder. Now, again, if you again, this is again a simpler example, and you'll come across many complex examples. So, but again, this is in itself many lines of code, but the constraint or the verification side is just one line, where it removes all the you remove all the computation and just focus on what's important, which is the constraints. So here is just one constraint where it's enforcing the division math formula. And now you just forget what QR0 and QR1 were computed to be. These are just some signals for you. You don't know anything about them because they are not constrained to anything, or at least they are not the prover can ingest any value to these signals. So now just focusing on this, you just think, does this ensure that QR0 and QR1 are quotient and remainder? And now with this, if you go to the division math formula equation, you remember that, okay, there's one constraint missing, which is the remainder has to be less than B, right? So again, I mean, it might be obvious to some of you, but at least with this code, you might think, okay, the remainder is A modulo B. Okay, so that's correct. But focusing on this just seems to some random values multiplied and added together. And then, yeah. then you constrain, okay, then you remember that, okay, the remainder was constrained to be less than P, which is the missing constraint here. So you add that on top of it. So this just helps you with mentally segregating both the sides and focusing on one thing at a time. So now moving on. So signal overflows, right? So as you might already know, ZK circuits usually operate on field elements. So usually every cryptography algorithm runs on some field element, which is numbers between 0 to P minus 1, whereas P is some prime. This is the same thing with EVM actually. Like EVM also operates on 256 bits, but that's not a prime number. So to give an example, like P here is a very large number. Actually, it's cutting off, but there's a whole array of digits below it as well. So if you, let's say, add 3 signals, X, Y, and Z, and constrain it to A, you can have multiple combinations of values for these 3 signals because, X plus Y can overflow over P as well. So for example, here I've presented 2 examples where 5, 7, P minus 1 will total to 11, and 5, 6, 0 as well will total to 11. And depending on your application, it might or might not be desirable. So just look out for these kind of bugs as well. And if you review ZK audit reports, this kind of bugs always come up where signals are overflowing. Now, why this kind of thing is important here, or more important here than EVM, is because in ZK circuits, if you're being exploited, you might not even know about it because, things are private here. So if your circuit has a bug, you might be getting exploited and you'll know about it months later, or may not even know about it ever. So instead, you already know about it. That's why security is important in general. So just take care of these kind of bugs as well. Another example here is if you're integrating your smart contracts with a circuit. So as you all know, EVM UNT size is 256 bits, but usually the default prime field for Circom and Ethereum is PN24, which has the prime field of bits 254. That means any signal in this Circom circuit cannot exceed 254 bits. But now if you are taking, let's say, a UINT, a Solidity UINT 256 as a public input to your circuit, it may exceed the range of your prime field. So you might be passing 255 or 256 bit size number to a 254 sized signal. So again, this is another common class of bugs where your UINT may overflow when passed to a signal, just because Circom signals are shorter in size. So an easy fix for this is that just ensure that whenever you are taking UINTs as a public input, just constrain them to be less than whatever your P value is. Usually that's called snark field in code bases I've come across so far. But this is another common class of bugs. Next is library integrations. So I touched upon this briefly before as well, but going back to my first point, documentation is super important because libraries may be missing some constraints to improve performance, because the lower number of constraints you have, the faster proving you have. And in that case, sometimes the library developers might leave it to the developers building on top of it to ensure that any preconditions or constraints are satisfied. So for example, I've come across some libraries where it's usually built for very high performance circuits, and they leave some important constraints to be satisfied for others to make sure that they are satisfied. And in the absence of any spec or documentation written for those libraries, it's easy to miss it. If you're a new developer, you may not even know of such peculiarities of the library. So to give you an example, here's if you're not aware of less than template, it's present in the Circom library, Circom lib library, developed by IDEN3 itself, who are Circom compiler developers. They have provided several helpful templates like less than or greater than and so on. So focusing on less than, less than takes a template parameter called n, which is like supposed to be the maximum bit size of the signal input signals passed. So less than takes two input signals, A and B, and it tells you whether A is less than B or not. So now if you create less than 2 and pass in 1 and P minus 2, it will tell you that 1 is greater than or equal to P minus 2. And that's happening because P minus 2 is actually greater than P 2 bits. Like it's really large number of bits, 254. So this is because less than doesn't constrain that the input signals it receives is actually R of n bit size. So yeah, this is just one example of such a library. And then the fix here is, first of all, if you're a library developer, just document what your assumptions are. And if you're a developer on top of it, just be aware of those assumptions and satisfy any preconditions outside the library. So here the fix could be to constrain the inputs out before calling less than, just constrain the inputs to n using another helper library present in Circom called num2 bits, which fails the verification if your signal exceeds a certain bit size. Right. So next is under constraint signals. So again, basically whatever I explained so far is an example of under constraint signals. It's really a broad category of bugs. And it's also the like most common seen so far. So for example, another instantiation of this kind of bug class would be a developer forgot to constrain an input signal. So now a malicious prover can inject any value for that and prove certain malicious or verify certain malicious things that are not intended to be. Then another like unconstrained signals in library is an example of that, or just plainly missing a developer might forget constraining a signal that like just plainly. So these are all examples of under constrained signals. And again, most common class of bugs. You have over constrained signals as well. This basically means that you are too strict on your computation and you are not allowing certain correct computation to be verified. This may or may not lead to bugs. I mean, in some cases it might be fine, but in some cases it might not let honest actors to interact with the system. So just be aware of this over constraint thing as well. It's less common, but it can happen and lead to rejection of correct computation. And finally, you have again, this is a common class of bugs, logic bugs. You can have it in your Rust code or like Circom code as well, but don't just directly jump to the code. Like it's always a better idea to review any design doc provided to you to ensure that that design is particularly safe. So to give you some examples, like there might be gotchas in the algorithm. For example, are you integrating with a smart contract correctly? You may, if you're reviewing ECDSA inside Circom, ECDSA has its own particular footguns. For example, you can make multiple ECD signatures for the same signer and same data, because there's the ECDSA algorithm takes in a certain argument called nullifier, and it's up to the signer to choose that nullifier. So if you choose different nullifiers at different points of time, you'll get different signatures. So again, it depends on the context. Is it safe? Do you want to prevent it? But you need to be aware of these kind of things when you're reviewing circuits. So for example, if you are going to allow any nullifier, you may be allowing multiple signatures for the same signer, and you may be allowing that actor to interact with the system multiple times. But let's say they are only supposed to interact with you once. So again, this is another class of bugs which you'll not find when you're reviewing the circuit, but you need to be aware of what algorithm the circuit is implementing at a high level. Then the another example is tornado cache or shielded pool. So suppose like you may have heard of shielded pools for 1 ETH, 100 ETH, or so on. But what if you allow arbitrary amounts to be deposited and withdrawn? So in this case, let's say, I mean, a depositor deposited some peculiar amount, and like take any random amount like 1.123 ETH, right? And now since the the withdrawer can withdraw only that particular amount, like 1.123 ETH, and it's not a common value that you'll see going in and out of your contract. So now it becomes very easy to link this withdraw and deposit, and basically now your privacy is broken, right? Because an external observer can link a deposit coming in and withdraw going out. So this, that the whole reason of your application, which is privacy, is gone. So again, this you'll not catch this while reviewing the circuit, but you need to be aware of this kind of bugs as well. And that's why I said, like, it's very important to review or to get peer review of your design very early on before you even start writing your circuits. Just because, I mean, the more time you spend on circuits, the more difficult it will be to go back and fix your design, and it's a whole lot of wasted work. Okay, so we are nearing the end now. There are many more classes of bugs, but I'll link you to some common collection of bugs that you can review at your own time. But again, just want to talk a bit about testing. So testing any code is important, but I'll just link some popular libraries that you can use to make sure your code is safe. So Circom Tester by Idem3 themselves is a popular testing framework where you can basically it lets you write unit tests where you can inject some particular values to your input signals and verify that your computation and verification is correct. Then you have Circom Kit. I think it's a newer library, but one good thing about this is that you can test your circuits using fake witnesses. What I mean by that is that in Circom Tester, you test your proving and verification the same flow. So basically, you prove some computation and then you send that same computation to the verification. So I don't think it supports proving or verifying an incorrect proof, for example, where you assign a signal some random value that is not intended to be there. So we call it witness. So you can assign some random values to your intermediary signal or an input signal. Let's say it was supposed to be 10, but you said, okay, assign this signal as 5 and then generate a proof. And then you can test whether your verifier will accept that or not. So it lets you test a broad variety of categories that way. And then apart from, unit testing framework, you have formal verification tools developed by Veridise themselves, like Coda and Picus, if I'm pronouncing that right. But we collaborated on a project called Circom Begin, where this library is supposed to support integers or signals that are more that have value greater than your prime field, because sometimes you may want that. So Veridise used these tools to find many more bugs in Circom. Some bugs were in Circom limit themselves. After that, there's Circumspect by TrailofBits, which is a static analyzer. If you've heard of Slither, it's something similar to that, where they don't run the circuits, but they have a set of rules that they run the circuits through. So it may be able to identify under-constraint signals and so on. So yeah, that's all in testing. Then certain resources. ZK Bug Tracker is really an awesome one. It is a collaboration between 0xSpark and PSE. And yeah, I'll just suggest everyone to go through it at least once to just know what kind of bugs you can have. I just present a small class of bugs there, but there are many more, especially in different parts of stack as well. It's regularly maintained, and if you find that some bug is not present there, feel free to make a PR as well. Then rest of the things are to make your theoretical background better. You may want to go through Moonmath manual, which takes you right from the scratch to make sure you understand how GROT16 works and so on. It gets a bit complex at the middle, but feel free to skip parts which you're not understanding if you don't have a background in cryptography, for example. But yeah, I suggest all of you to go through it at least once. Then I also wrote some basic stuff on elliptic curves. It tells you how it again starts from scratch and tells you how Ethereum public keys are generated. It's again based on elliptic curves, and it should be a much simpler read than the other things on this slide. Then you have Reascal ZK book. Again, it's a very extensive resource, a collection of different blog posts, which probably lets you on the same path as Moonmath Manual, but probably focused towards developers. So yeah, I think this is the last slide. That's all from me. Happy to answer any questions or any feedback.
All right, thank you so much. I guess do we have like any? That was a great lecture. Do we have any questions for Blockdev?
No pressure, yeah. Yeah. I think Veridise will be able to answer it, but I think Z3 is definitely one of the SMT solvers used in Coda Picus. But I myself have to become an expert on those tools. I haven't used them much, but I believe Z3 is one of them. But yeah, if anyone can answer here, probably from Veridise.
We actually use CVC5 in Picus because they have a finite field solver specifically for solving equations over finite fields. But it does support both.
All right, I think that's it.
Okay, yeah, thank you again so much. And that was like really helpful, and I hope everybody enjoyed it, and I hope you got like more tips for the subsequent quizzes, especially for the people participating at the race. All right, thank you so much. See you guys later.
Yeah, see you. Bye.